hopefully. Awesome. All right, so today I just wanted to run through the Thermochemistry exam and just point out some key mistakes and also help you guys understand the marking schedule. You guys will be able to take your mocks home probably on Friday. Well, definitely on Friday because it's the end of the week. And what I'll do is I'll also post the marking schedule. I'm just holding off and doing that because I just want to make sure all the grades are finalized and everything else. Anyway. Cool. Let's talk about this thermochemistry exam and kind of quickly breeze through it. This first question was really standard. It was just your electron configuration. This one only went up to an achieved, and you need to get 2 out of 3 for that one. 2 kind of areas of mistakes. Chromium is an exception to the rule. A lot of you guys lost points because you forgot that. The nickel, some of you guys got wrong because remember it's a transition metal, so you should be taking it off of the 4s first, not the 3D. So that's where a lot of you guys lost the point there. And for some reason, when you guys, I think that's tin, you guys misread this and you grabbed the wrong element on the periodic table. A lot of you guys read the I as an L on the periodic table, and so you grabbed a totally different element and did a really weird thing. I can grab a periodic table and show you what you grabbed by mistake once I find my periodic table. Here we go. You guys were supposed to grab, once I find it. That's the one you guys grabbed by mistake. This is the one you guys should have grabbed. Oh, you guys can't see it. There we go. This is what a lot of you guys grabbed. This is what you should have grabbed. That was just a silly kind of reading comprehension error. So watch out for things like that. Remember, that was an L, not an I. Some of you guys misread it. Cool. All right, this question here was starting your periodic table trends. The first thing here was to make sure you paired the right number with the right element. Most of you guys were fine on it. The thing you have to, most of you guys were fine with the phosphorus because you looked at the periodic table and you're like, phosphorus is over here. It's going to have the highest numbers. So most of you guys had no issue pulling that number for me. But the problem is, again, you needed 2 out of 3 to get that right. So the mistake then happened with the sodium and the potassium. So remember, the trend, as I go down the periodic table, my atoms get larger, I'm getting more shells, there's going to be more shielding effect. As those atoms get bigger, they have a less of attraction to those valence electrons. So you should have ranked potassium as the lowest and then sodium as the middle one. So some of you guys just got that the wrong way around. You should have noticed that the sodium and the potassium are very similar, and that makes sense because they're both in that first group together. So they both have 1 valence electron. Are we good so far? The problem with this one here is that if you guys matched them incorrectly, it then snowballed and affected your long answer. Do you guys see what I mean by that? So it's really important that you know the basics, otherwise it's going to hurt you elsewhere. This one here, most of you guys were fine. So the achieved point was just correctly stating a factor affecting ionization energy. The merit, I've given an extra way to get that merit point because some of you guys didn't get either of these 2. The trick with this question was pairing it well. So a lot of you guys just talked about all 3 and then just kind of just went through a list. But what I was looking for, and this is what the marking schedule was looking for as well, was that you were pairing them well. So you should have paired sodium and phosphorus together because that was your comparison for the period, aka your row. And then you should have paired the sodium with the potassium because that was your comparison for the group. Does that make sense to everybody? So that's what we were looking for comparison. There wasn't really much you can do with the phosphorus and potassium because they're different groups and different periods, so they're not easy to compare, and that's not what they looked for in the marking schedule anyway. So for the merit, what we're looking for then is, did you compare the group comparison, so potassium and sodium, or did you compare the sodium and phosphorus, because that's your period comparison? So long as you got one of those, you got the merit point. I did, however, add an extra way you could get that merit point. And that's if you did the trends for both of them, but you're missing some sort of layer in your answer, because I figured if you could tell me both comparisons, but you forgot something, then it was fine. For the excellence, you got to have everything. The other thing that you needed for the excellence was that I was looking for the electron configurations. And you can see that on the answer here. They wanted you to talk about their electron configurations. I wasn't specifically necessarily looking for the fact that you wrote out the electron configurations. What I was primarily looking for was if you talked about how the group both have one valence electron, whereas in the row, they both are ending with period 3. Does that make sense? So that's what I was specifically looking for the excellence, because it was added into that question. It's quite unusual. Normally, they don't ask for this level of detail, but it is useful to have because then you can add it as a final kind of layer. So for example, when you're thinking about the group 1, they have one valence electron. And since it only has one valence electron to lose, think about the stuff we learned back in year 11. It's very easy to remove that one valence electron because if they drop down a shell, they're now stable. So it's quite easy to take away that electron. Whereas in this case, we're dealing with one valence electron versus 3, and phosphorus is less likely to give up those 3 electrons because it can get stability in other ways. So do kind of keep that in mind with that comparison. Does that make sense? So it was just an extra added layer. It's quite unusual that they asked for that. It's useful to have it just to kind of polish your answers. But it's unlikely that they'll have that on the actual assessment. Cool. Next one here then was your Lewis structure and shape question, and then you compare and contrast of those two shapes. I think you were mostly fine for this. The main thing that was kind of silly was you guys didn't read the question. A lot of you guys wrote about polarity because you're like, I see that I have 2 Lewis structures and shapes, and you're used to writing polarity. There was no points for polarity. It was a pure shape question. So make sure you read it. That was where a lot of you guys got let down. So just as a reminder, you're looking at the VSEPR theory and you're explaining the regions, you're explaining about bonded and unbonded pairs and how that influences the shape. So do kind of keep that in mind. A lot of you guys, like I said, misread the question and wrote about polarity because you were assuming polarity. Again, I tried to make the marking schedule a little bit kinder. So the original one was you have to fully get a shape and a Lewis structure. I said if you got 2 shapes right, so you wrote these 2 down, or you got 2 Lewis structures right, I was going to give you the achieve point anyway. Cool. And it doesn't need to come from the same molecule is what I was saying. So that gave you some little flexibility. I was also flexible on those bond angles things because I said in the past they're unlikely to ask that because it's just a weird memorization stuff. So I wasn't too fussed on that, but I was looking for a shape kind of justification. A lot of you guys wrote polarity justifications. The last question here was your polarity question. So do make sure you read it so you know what you're doing. So this one was your chlorine dioxide, and they wanted you to talk about polarity in this case. Cool. So this one only went up to the merit level. Remember, whenever you're talking about polarity, you really need to justify what polar bonds are. Otherwise, you don't get the full layering. Again, I created another way to get that achieve point because I'm mindful some of you guys forgot to talk about polar bonds. It's very often that you guys do forget that layer. So if you told me about something about symmetry, I was still willing to accept it. The tricky thing about this molecule that I gave you, Lewis structure-wise, was that it had only one, it had a weird odd number to work with. So let me just look up, what is it, chlorine dioxide. And just pull up the Lewis structure is what I want. Bless you. Here we go. So when you did the Lewis structure for this guy, if you guys did do it, you would have noticed it was a very strange looking molecule because you had that weird kind of lone pair, or sorry, you got that weird 1 electron there because it was an odd number. you would still count this as its own region. So chlorine has 1, 2, 3, 4 regions of electron density. It would be a bench shape. And because of that bench shape, that's going to result in the unequal distribution of charge. So a lot of you guys misidentified this as a nonpolar molecule because you thought it was linear. It's actually bench shape. And then, like I said, it's the same kind of justifications that you normally would have, explaining what electronegativity is, explaining what polar bonds are, and then explaining the symmetry, and if that cancels out the dipoles. Are we okay with that one? That one only went up to a merit anyway. So it was a very strange molecule. It threw a lot of you guys. All right, next one. Trying to breeze through this so you guys can see everything. All right, this one here was your enthalpy calculation. Most of you guys were fine on this. A lot of you guys struggled with definitions. So standard standard enthalpy of formation. Make sure you guys know your definitions. In this case, be very mindful that we're looking for the energy change. Don't say required because you don't necessarily know if it's an exothermic or endothermic reaction. So you might have seen on your paper I wrote required or released, or you can just say energy change because that encompasses both possibilities. You don't know, like I said, if this is an endothermic or exothermic reaction, so you shouldn't specify what's happening to the energy. Does that make sense to you guys? The other thing is when 1 mole of substance, a lot of you guys wrote compound, let me backtrack. A lot of you guys wrote molecule. Molecule is probably too specific of a word to use in this instance because not everything that's forming is a molecule. It could be, for example, an ionic substance, which isn't a molecule. So just kind of be careful with your word choices, but I was pretty generous with what I was going to take for the achieved. State it's under standard conditions and state from their elements. The other thing you could state is from their constituents, because if you said constituents, then you're referring to the fact that you're pulling it from the elements. Cool? The other thing for this, so this one did go up to merit point. You had to get this equation. A lot of you guys just mucked up this equation, revised this material, because I did do a lesson on it. Basically with the formation, you're taking 1 mole of the product and then you're backtracking and figuring out the ratios for all the little elements that make it up. So you should have elements on that left-hand reactant side. Cool? The other place that a lot of you guys made a mistake was on the nitrogen. You just wrote N. It's nitrogen gas, it's N2. And then for the achieved, if you forgot your states, I was willing to still give it to you, but for the merit, I was looking for the states. So keep that in mind. We good? All right.
Wait, could you just read out the definition?
Yep.
For the vaporization.
Yep, and I'll zoom up so you guys can see it. So the enthalpy of vaporization. Oh, are you talking about part B? This one? BI2? Yeah. So this one here was a nice kind of theory question, and what they're trying to ask you is why is vaporization going to require more energy than fusion, which is melting? You have to think about back to year 9 where we're doing states of matter. When you melt something into the liquid form, there's still some intermolecular bonds that are occurring because it's just sliding past each other. So you're not doing that full breakage of the bond. When you are vaporizing it and you're turning it into a gas, all the bonds are completely broken. So since we're completely breaking those bonds, it's going to require more energy. Does that make sense?
Yes.
And I'll show you the definition here. So yeah, enthalpy of vaporization is referring to the fact that we're breaking all the attractive forces between the liquid particles to form the gas. When we go from solid to liquid, we're just breaking some of the attractive forces.
Yeah.
So that's the reason why.
Would you call them intermolecular?
Yeah, intermolecular forces. You can also say attractive forces. They have that here. In this case, you wouldn't need to specify what type of intermolecular force because it's just a general statement. But since they did give you butane, it's a nonpolar molecule, so you would be talking about temporary dipoles. Cool. Alrighty. Next one. Okay. This one here was your easy Hess's law. You could have used the shortcut. And I can tell really quickly that I can use the shortcut because everything they've given me is in the formation enthalpy. So you didn't need to do the full Hess's law and write out the equations for that. And I think most of you guys picked that out and you didn't do the full Hess's law and writing the equations. It saved yourself some time. The mistakes, however, though, looking at it, so here were the numbers for each one. You basically just needed to make sure that you multiplied it correctly from the coefficients in front. The main thing that you guys forgot as your final step, though, is that you have to do the sum of all the new bonds that are formed, that energy released, and then you need to minus that enthalpy value that they gave you here. So that was where the mistake was for a lot of you guys, was just you forgot that final step. Are we good? Questions, concerns, comments?
So if you went 1,500 minus the other.
If you had the wrong way around, you would have gotten the opposite sign. Yeah. So it was weird. You guys haven't seen it in this format before, because usually what we do is give you the reactants and the products.
What was the enthalpy that we were meant to?
226, negative 226.
What about the one that we had to minus the other one?
So what I was looking for was correct, process correct, but error in the calculation with the equation. So like, for example, you forgot that. So you would have had this answer here and stopped.
So the 715 would have been one.
Yeah, so if you had forgotten to do that final subtraction, I think you guys got negative 1,795 as your answer, because you forgot to put in that last bit.
Can you explain the process, like for each formation equation, how many numbers were meant to each one, right?
Yeah, so that is having to do with the coefficients that you got over here. So that 3, that 1.5, and that 3 again. So for the nitrogen dioxide, you should have multiplied this number by 3, that 34. For the carbon dioxide, you should have multiplied it by 3 again. And then for the water, you should have multiplied it by 2.5. Because you're just taking the coefficients from the equations.
Right, and then with those answers, you minus them.
So you would add all those enthalpies together, because that's the energy released from the new bonds that are formed. And then you would have subtracted away the enthalpy from here, because that's the energy required to break the bonds in all these guys here. Is that?
Which one do you put the bigger number in?
So you have to take the reactants, sorry, you have to take the products and subtract away the reactants. And so since this reaction here is the combustion of the nitroglycerine, you could use the enthalpy value here, because that was your value for energy that's required to break all the bonds in the reactants. Does that make sense?
Yeah.
So that's the step that a lot of you guys missed. Yeah. It was a very different format to what you guys usually get as a question.
When you times it minus 286 by 2.5,
yeah.
What value did you use?
You should get 715.
71.5 or just 7.5?
715 is what you should have gotten. If I can find my phone, I can do the math and double check it. So it was good. I've found mistakes in their math before. So what was it? 286 times 2.5. Yeah, you should have gotten 175. Or sorry, 115. Sorry, 715. It was a weird question.
Oh, so we would go 715 minus 1529.
So you should have used the signs that were on for those each enthalpies. So the 34 was positive because their enthalpy value is positive. The carbon dioxide formation is a negative number, so you keep that negative. And then the formation of water is also negative. So you should have had positive, negative, negative. All of these add together. You should have gotten a negative number for that. And then you're subtracting away another negative number, so you're just adding it. And that's how you got the negative 266. Does that make sense?
Sorry, negative 266 or negative 226?
Sorry, negative 266. I have a hard time reading numbers for some reason. Whatever's on the paper is right. Does that make sense? It was a very, like, you guys haven't seen this style of question before.
For some reason, I thought we were meant to minus them.
No. So you have to think about it as in groupings. You think about this section here. This is your products, and that's the energy released when you make the new bonds, and then you subtract away the reactants because that's the energy that you need to break all those bonds. So energy released subtracted from the energy required. And then that gives you a net value. Yeah. The other way you could have done it is probably through using the long way of Hess's law and actually writing out all the equations. All right, next one. Cool. All right, E was a tough one for you guys because it was your entropy question. And in this case, what you really needed to think about was the balance between the enthalpy and the disorder. So the heat energy and the disorder. In this case, it's an endothermic reaction. We're going to be using Hess's law. And we're thinking about that comparison of it's going to absorb energy, but what's the disorder that's going to be caused when this reaction occurs? The other thing you need to think about, and I think it was also stated in this question, no, it didn't. Okay. The other thing you need to think about with these entropy questions is the disorder. So disorder within the system of that chemical reaction and the disorder to the surroundings of basically that absorption of that heat energy. So 3 things to consider. First off, this is an endothermic reaction. It's absorbing heat energy. We think about Hess's law and how that's the beginning part of my equation. Then we think about the disorder. We think about the disorder in the system, and we think about the disorder in the surroundings. In the system, with that state change, or with the dissolving, I should say, it's increasing the disorder. So we started from a solid particle, and then we dissolve it into a liquid, and it's become aqueous. A lot of you guys wrote that it became liquid. Be really, really careful. It's not becoming liquid, it's just dissolving into the liquid. So aqueous is more disorder than the solid. So that has increased the disorder within the system. The other thing you need to think about is that since it's an endothermic reaction, the surroundings, those molecules are going to now move slower because that heat energy was absorbed, and so they don't have that same kinetic energy to move around. So surrounding-wise, the disorder will decrease because those molecules aren't moving as crazy. But the net balance is that the dissolving must be spontaneous because the entropy that is caused in that disorder of the system is greater than whatever the entropy of the surroundings, becoming more ordered, and the enthalpy of the endothermic reaction. So think about, like I said, Hess's law, and you're thinking about that delta G equals your delta H minus whatever the temperature is and the entropy of the surroundings. Does that make sense?
Wait, so you're saying the entropy of the surroundings?
So with this entropy of the surroundings, the entropy will decrease. It's becoming more ordered because the surroundings are getting colder because it's absorbing that heat energy because it's an endothermic reaction.
Yeah.
But in the system, so in the actual dissolving of, I think, what was it? Ammonium nitrate? Yeah, ammonium nitrate. That's increasing because you're going from a solid that's very organized to a dissolved ion, which is very disordered. So when we're looking at the net results, this is an endothermic reaction. Even though we have the surroundings decreasing in entropy, the system is increasing in entropy.
Yeah.
This is a greater change than this one. So this can counteract whatever is happening to the surroundings.
But what's a greater change?
This one. So this is a greater number. This system.
The system.
Yeah.
So we're basically saying that the entropy of the system is greater than the
Yes. Yeah. And even though it's an endothermic reaction, it's still spontaneous because of that. Yeah. So all these factors come into play. It was a really hard question. Usually you don't have it this hard, and usually it doesn't go up to an excellence level, but in this case, because you were talking both about the surroundings and the system, it did go up to an excellence. Okay? There are a lot of questions in here that you guys haven't seen before in this format. So it was a little bit hard. All right.
Do you have to explain why spontaneous?
Yeah, that was the whole point of that question.
So like everything you just said was the reason.
Yeah, why it was spontaneous. Yeah. Cool. All right, last one here was question number 3. I really liked question number 3. So this one was your urea. A lot of you guys lost the points because you did not read the question again. So it wanted you to identify all the intramolecular forces and intermolecular molecular forces. A lot of you guys listed these without any problem, but you forgot about this guy. So with the intermolecular forces, there's going to be temporary dipoles in everybody, because that's what you get with the electrons. They just spontaneously congregate into an area. So everybody has temporary dipoles. The permanent dipoles are only in polar molecules. So you have to ask yourself, is this a polar molecule? The answer is yes. So this one does have permanent dipole-dipole attractive forces. The last one in that list is your hydrogen bonds. So does this one have hydrogen bonds? And the answer is yes, because we have a nitrogen with a hydrogen. So you should have had all 3 intermolecular forces listed. Most of you guys did that without any issue, but you forgot that this question also wanted the intramolecular forces. So basically listing out that there's a covalent bond. Be really careful with which one you're referring to. So when we're talking about any phase changes and things like that, you're talking about the intermolecular bonds, because remember, it's between the bond molecules that have those attractive forces that you need to break. If you are breaking a covalent bond, you are doing a chemical reaction. Cool? All right. This one here was asking about solubility, and then they had a drawing for you guys to do. This was a nice throwback to level 2 chemistry, when you guys had your solubility questions, and you're thinking about the attraction to self versus the attraction to water. With this here, you just need to identify what bonds were being broken in that dissolving or mixing process. And there was a nice little or option there, so you didn't need to have all of them. The other thing that they were looking for the achieve was a correct diagram. And then for the merit, it was just making sure you had both bits of information. And you also covered hydrogen bonds in detail. So what I will do is I'll draw out this molecule, because a lot of you guys struggled with drawing it and figuring out how it relates to that dissolving process. It's basically a more complicated ion dissolving question. So if you guys remember last year, you very frequently got that ions dissolving in water, and why is it soluble in water, and then you showed the ions kind of being surrounded by the water molecule. It's the same principle. So draw your urea, which is this guy here, and draw it completely extended, so that way you can see everybody. Then go through and write in what is going to be slightly negative and slightly positive. So oxygen's very electron negative, that's going to be slightly negative. Nitrogen's also very electron negative, so that area will also be slightly negative. And then the hydrogens are going to be slightly positive. So that is how the dipoles would have distributed in that molecule. Are you okay with that? Actually, I should have done that in a different color because it would have helped. Too late. The next thing you need to do then is draw your water molecule. So if you guys remember with water, that's slightly negative and this end is slightly positive. So you just need to line the molecules up so that way the positive and negative match. So for example, if I was trying to draw this up, what I could do is put the oxygen there, the hydrogen there, so that way the negative oxygen is aligning with the positive hydrogen of my urea molecule. And then the hydrogen of the water is slightly positive, and it's aligning up with the negative of the nitrogen. And just kind of draw some water molecules to kind of go around it. So like over here, I could have drawn another water molecule. Again, with that, whoopsie, it should be the other way around. With the hydrogens on this end and the oxygen on the other end. So that way, again, the positives line up to the negatives. Does that make sense to you guys? Move that down. It was a hard molecule to draw. I'm not gonna lie. Just watching the time. Does that make sense? But it's basically what you guys were used to doing when you did the ion question. If you guys remember from last year, you would show the positive ion being drawn, and then you would show the water molecule around it. It's just that, but a more complicated version of it. Does this ring a bell? You're just doing that, but a more complicated one. Yeah? All right. This one here is your heating curve. This was a throwback to year 9 science. We asked this question on your test. So these points here are your states. So solid, liquid, gas, and then the flat lines are representing the melting point and the boiling point. The thing about this question here was asking about, why do you have this kind of straight line here, and explain all the different points of the graph. The B part is really important because when we're thinking about B, we notice there is no temperature change. And the reason why we don't notice a temperature change is because instead of that energy, that heat energy going into the molecule's kinetic energy, it's being used to break the intermolecular forces so that way it can change state. So all through this point here, the energy is going in, and it's going into the particles. The particles are allowed to move faster, and that speed of the molecules moving is what we measure as temperature. I hit this point, which is my boiling point, and at that point, I don't notice the temperature of the water increasing anymore because that energy is instead being used to break up the bonds. Then I go into the vapors, and now the vapors can increase energy because now the particles have broken all the intermolecular bonds, and the particles can now absorb back that heat energy and do that kinetic moving again. Think about food. Think about why we steam food versus boiling food. We steam a lot of food because the temperature of the steam is hotter than the temperature of the boiling water. So that's why you see a lot of food being steamed. All right. Trying to move through it quickly because I know the bell's going to go soon. All right, this one was your compare and contrast. This one was your phase change question. And this one here, the main thing that you need to think about. So there's going to be different varieties of how you're going to answer depending on what molecules they've given you. Since they've given you 2 things of the similar masses, the intermolecular forces are going to be basically similar. So they both have the same intermolecular forces. Or sorry, not intermolecular forces, temporary dipole attractions. They're both polar molecules, so they're both going to have the permanent dipoles. But the reason why these guys have such different temperatures is the hydrogen bond. Yeah? Most of you guys did name the hydrogen bonds as the reason for their difference, but the problem is that I couldn't give you higher points unless you used all the attractive forces involved. So I couldn't give you the excellence point unless you also talked about the temporary dipoles being roughly the same because they're roughly the same mass, and if you forgot the permanent dipoles that they both have. Does that make sense? It really depends on the 2 molecules that they give you. So they could, you guys have seen, they give you bromomethane versus bromine gas as a common kind of pair. And in that case, this one has a really large molecular mass and this one doesn't. And so the mass of this one, the temporary dipoles, is the important reason why this one has a higher boiling point. Does that make sense? So you got to pull the right information for what the molecule they give you. In this case, they had similar masses, so the main thing you are using as your difference point is that hydrogen. Cool? All right, and then the last one here was your Hess's law calculation. I'll just put this one down so you guys can see the summary. The main thing was thinking about, do you keep the equation as the same? Do you need to flip it? Do you need to multiply by 3? Most of you guys were fine. You figured out that this one needed to stay the same, that one needed to stay the same, and the water needed to be flipped. But a lot of you guys forgot to times it by 3. And so your number was off. So you need to times it by 3 because when you are looking at that equation, so here's my water formation, and then I need to be mindful that the hydrogen gas is 3, So I need to match it. And same thing with the water and, or not the water, the same thing with the oxygens. That's a half, whereas you're trying to get rid of 1.5. Do you see where that 3 came from now? The top equation. Yeah, so you will still get the top equation. The problem is with this bottom equation here with the water formation, it's not enough to cancel out the hydrogens and the oxygens from the other 2 equations.
So you need to look at all of this.
Yeah, yeah. So what you should be doing is your net result should be this equation.
Yeah.
But you shouldn't be you can manipulate this looking at that equation, but the problem is, in order to get rid of these hydrogens and oxygens, you need to multiply this one by 3. Does that make sense? Yeah. So just lots of kind of silly mistakes that kind of added up, and there's a lot of tricky things in this assessment that you haven't seen in other assessments. So I would say this is like a reasonably difficult mock that we gave you. All right. Any other questions? Yeah.
Is that like longer than
I don't think so, but there were some tricky questions in there. So tomorrow I'll do the organic mock. All right, can you please return the thermochemistries to me? Some of you guys have organic, so can you hand back the organic as well? If you have any evidence of work, please put it into my box. And I think that's basically it for today. So I want the mock that you wrote on the mock, but if you have a spare paper that you're just writing notes, you can keep that one. So.